Well, there we go. I think I got it. Unplugging the document camera and then plugging it back in.
Have you tried turning it off and on again?
Well, I've done the turn it off and on again. I haven't done the unplug. So after about 30 minutes of connectivity issues with my microphone, I finally got settled into this. We're focusing on a Type 10 problem, which is a sequences and series question. This is from the year 2016 on the Calculus BC exam, and we're going to walk through it. So let's go right ahead. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 equals 1 and f prime of 1 equals negative 1/2, and then they give the nth derivative expression evaluated at 1 for all derivatives greater than or equal to the second derivative. Write the first 4 non-zero terms of the Taylor series. So the first thing I'm going to do is write out a general Taylor series formula, and then we're going to build that from there. So let's add that in. Okay, so our function can be rewritten as a Taylor series, and I haven't shown the general term in this, but we do have the first 4 terms. And what you can see is each time f, then f prime, f double prime, f triple prime, and then we have x minus c to the first power, x minus c to the second power, x minus c to the third power, and on and on. And then likewise we have the over, if you want to think about this as over 1 factorial and over 0 factorial, you can. But we have the first 4 terms here, and we're going to use this to translate our function. So f of c for us, we're going to say we're going to let f of x equal f of 1, since we're centering our Taylor series at 1. F prime of c is negative 1/2 times x minus our center. I'll go ahead and put that to the first over 1 factorial. Our second derivative we would need to evaluate using this rule. So our second derivative when c equals 1, or sorry, when n equals 2, we're going to look at this and we're going to get 2 minus 1, which is 1 factorial over 2 to the 2. So that's 1/4, and then it's going to be a positive. So we have 1/4 x minus 1 squared over 2 factorial. And then our third derivative, this would be where n equals 3. So n equals 3 gives us a negative, so there's our alternator there. And then 3 minus 1 is 2, 2 factorial is 2, and then 2 to the third is 8. X minus our center to the third power over 3 factorial plus dot, dot, dot. And this is our Taylor expansion for this function. Maybe I should write that as t of x. It's maybe could be cleaned up a bit, but it gets us the credit for the AP test. They do say write the first 4 non-zero terms and the general term of the series. So I'm going to pause the video and clean this up a little bit so that it's easier to talk about what the general term of the series looks like. Okay, so this is cleaned up. As you can see, we've got the alternator in here, which comes from this negative 1 to the n. Our numerator has n minus 1 factorial, 3 minus 1 factorial, 2 minus 1 factorial. Our denominator has 2 to the n, so 2 to the third, 2 squared. And when we look closely, we have these factorials stacked on top of one another. And so in the process of simplifying the expression, terms will cancel out, and we can have 1 factorial is pulled out of 2 factorial, so you have 2 times 1 factorial, and the 1 factorials cancel. 2 factorial is pulled out of 3 factorial, so we have 3 times 2 factorial, and the 2 factorials cancel. And so from there, we should be able to deduce what our rule is, our general term for the Taylor series. There's an alternate in there. There's the alternator. Our numerator has x minus 1 to the nth, 3, 2, 1. And our denominator has 2 to the nth, as well as our n value, so 2 to the nth times n. And there's our general term. Okay. So our Taylor series with the general term is listed there. If we want to count up points as awarded by the AP test, the first two terms would get you your first point. Getting the third term correctly gets you your second point. Getting your fourth term correctly gets you your third point, and then getting the general term gets your fourth point. Did I say 4 there? All right, well, 4 points total, which is pretty impressive for Part A. Now, please note for the COVID-19 2020 test, I believe creating Taylor series is off the table. Actually, I don't recall. I'd have to look that up. Let me do that. Okay, from my understanding, it does look like that finding Taylor polynomials is part of the 2020 reduced exam. So let's move on to Part B. Part B says, the Taylor series has a radius of convergence of 2. Find the interval of convergence. Well, we've already established that the center of the Taylor series is at 1, and if the radius is 2, then that means we're going to go 2 above the center and 2 below the center, and this is our interval of convergence. We just need to determine whether we include the endpoints or do not include the endpoints in the process of identifying our interval of convergence. So we are going to test when x equals -1, and we're going to test when x equals 3 to determine whether or not those two things would be part of the interval of convergence. So if we have our general rule as established in the previous problem, there's our Taylor series, and we want to test when x equals -1. So if we're going to test this when x equals -1, we're going to get the expression, oops, -1. -1 minus 1 is -2. And if we simplify that expression, this alternator cancels that alternator, and 2 to the n over 2 to the n cancels, and we arrive at the harmonic. And we should remember that the harmonic series is divergent. We know the harmonic series is divergent by the p-series test, p equals 1. So conclusion, we're not going to have a hard bracket, we're going to have a soft parenthesis for -1. Now we're going to repeat this process again for testing x equals 3. Three minus 1 to the nth is 2 to the n. And then the denominator has no x's in it. We see the 2 to the n's cancel. And we finish with an alternating harmonic. And so this is by the alternating series test, or by our recognition of alternating harmonics, we should be able to draw the conclusion of convergence. So it converges when x equals 3. So on the hard bracket, we put that on the 3. So our interval of convergence goes from -1 excluded to 3 included. This is worth 2 points. Your first point comes from recognizing where the endpoints are. So recognizing that the endpoints are at -1 and 3, which is actually pretty nice because you could have gotten that even if you didn't solve anything in part 6, just by recognizing the center is at 1 and the radius is 2. Your second point comes from everything else, doing the analysis to draw the proper conclusion. So, oops.
Russia is a democratic federation.
All right, moving on to part C. The Taylor series can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms. So if you recall, f of x can be approximated with the Taylor series, and this time what we're going to do is just do the first 3 terms, which would be the second degree Taylor polynomial. And if we consult part A, we can see that the first 3 non-zero terms times 2. So there's our first 3 non-zero terms. We're going to approximate f of 1.2. So f of 1.2 can be approximated by t of 1.2, or t sub 2 of 1.2. And when we plug those numbers in, 1.2 minus 1, and then 1.2 minus 1 squared over, I'll go ahead and write that as 8. And this is a numeric answer, and numeric answers are good enough for credit on the AP test. If we actually wanted to go through and simplify this, 1 is 1, 0.2 cut in half is 0.1, and then 0.2 squared over 8 is so there's our decimal approximation. The function at 1.2 is near 0.905, or at least our Taylor polynomial predicts that it's near. This is the first 3 terms, which is the second degree. Okay. This is worth 1 point, and that first point comes from, did you get the approximation correct? I encourage you to always stop once you get to the numeric answer, rather than push it along and possibly make an arithmetic mistake. So a good test taker stops there. A good mathematician does all of the work. All right, and then finally part D. Show that the approximation found in part C is within 0.001 of the exact value. So what we have here is an alternating series, and we've learned that with an alternating series that the maximum error is going to be, I'll write this down in words, the maximum error is going to be less than or equal to the absolute value of the first unused term. So what we want to do is consider that we've used 3 terms, and the first unused term would be the 4th term of our Taylor polynomial. Max error, as you recall, is going to be the difference between the function and the approximating polynomial. So this difference here refers to the maximum error. Maximum errors are, of course, consider to always be positive. So we want to take the absolute value of that difference. And this will be less than the first unused term. And if we consult our previous work, the first unused term was the x minus 1 to the third power over 2 to the third times 3. Make sure I got that right. There is a negative in there technically. Okay, so the x minus 1, in our case, we're looking at 1.2, so we can write 1.2 subtract 1. And that gives you the value of the first unused term. If we want to go about simplifying that, we're going to get a value of 0.2 to the third over 8 times 3. And we continue simplifying that further. 0.2 to the third would be 0.008 over 8 times 3. And this is equal to, the 8's cancel, and we get 1/3000th. And 1/3000th is smaller than 0.001. So 1/3000th is smaller than 0.001. So our error, the maximum error we have is 1/3000th, which means our previous answer was within 1/3000th of the true value, which is definitely less than 1/1000th of the true value. This is worth 2 points. The first point comes from the error form, so recognizing that error is less than the first unused term. And then the second point comes from the analysis, which I would interpret as actually going through the process of evaluating this, and particularly recognizing that the value is less than the desired 0.001. All right, thank you for watching. Be sure to comment, like, subscribe, throw money into my Bitcoin wallet, mash that like button, and maybe I'll hit a face reveal around 100 subscribers. Woot woot.